But then again, like, you might get that. You might not like be telling everybody that. Because there's one thing that's on these classes.
This is a very easy chapter. Alright? The name might be a little frightening, but the concept is really easy to absorb. Let's assume that we have two inductors that are magnetically coupled. Alright? Magnetically coupled means the flux of one inductor will move through the winding of another inductor. Alright? So when this changes, the flux of this changes, there's a voltage that's induced in the other one, and vice versa. So any variation in the current in here will induce some voltage in the other one, and vice versa. Alright, so I'm going to add a current source to this one to show a current that's IS. And it's a variable current. Any current in the circuit, okay, this represents that. And I have V1, the voltage across this inductor here. The current that goes in, which is in this case equal to IS. The current that goes to the other one, and that's I2 from the rest of the circuit. And here's points C and D as opposed to K and B. Okay? So this entire thing is a two-pole circuit. Call this a two-pole circuit. That means you have two elements off of it, two voltages, two currents, a voltage and a current. Okay, on the two sides. Alright, but the voltage and current cannot be on one side, because that's a one-pole circuit. The two-pole circuit, voltage and current should be on the different sides. Alright? Now, let's assume that IS is 100 cosine of 3t ampere. We want to find V1 and V2. We want to find out what those voltages are if the elements are given as this. Okay? So, we have L1, inductance of the first inductor when the second inductor is open circuit. When you open circuit this part of the circuit, there's no current in here. There is no effect of that part to this side, and there is no effect of this to the other side, because there's no current that can flow. So that is where L1 is measured or calculated, as if this is removed completely. So L1 is given as 4 ohm. L2 is when you open circuit the first side and measure the inductor from this side. So essentially, the flux that links this side is not effective. There's no current that can flow, and the voltage does not have any effect on the voltage of the other side of the circuit. That's where L2 is defined, and that's 16 henries. Okay? Now, there is a mutual inductance, and mutual inductance is the amount of current, the amount of flux that links this, because of the current in that one, divided by the current of that one. In other words, if you inject some current from here, and you have some flux in here, you divide this flux with this current, and that's M. Okay? And if you do it from the other side, you inject some current, you have some flux over here. You divide this flux with this current, and you get the same M. So M is the same if you measure from two sides. And that's why it's called mutual coupled. That means from two sides, you have that same value. Now, from these, V1, which is the voltage in here, is going to be L1 di1 over dt. That's due to the self-inductance. So some flux causes this voltage, and there's some flux on the other side. So flux M di2 over dt. So that's the effect of the other flux. Same way, for voltage of the second part, you have L2 di2 over dt plus M di1 over dt. That's all much you need to know about this magnetically coupled circuits, okay? Because in your mesh analysis, you're going to replace voltages by these two equations rather than only a inductance over here. So there's an effect of the other inductance. Okay. One thing is, if you have an open circuit on the right coil, okay, that means this side of the circuit is open. Then what you have is I2, there's no I2, I2 is 0. Okay, and here I2 is also 0. The voltages are like this. Voltages are V2 is equal to, you ignore I2, then you have L1 dI1 over dt. That's V1, sorry. And V2, there is no I2, so that effect is gone. You only have an effect on the current on the first side, or the left side. That's M dI1 over dt. Okay? Now, because the current is known, I1 is known, I can actually go ahead and calculate that. So L1 is 4 V over dt. That's 100 cosine of 3t. Sorry. Okay? And this is equal to 400 multiplied by 3 is actually 1200 minus sine of 3t. Okay? Same way, with V2, you have 2d over dt of the same current, I1. And that's equal to 600 minus 600 sine of 3t. Okay, all I did was, I have current IS, which is equal to I1. So I have I1. Put I1 here, take derivative, and multiply by the self and mutual inductance.
For
M is, for some reason I make it 2. It has to be 6. Oh, sorry. I mean, this is 16, this is 2. That's right. Thank you for correction. Yeah, that's 2. Okay. So, let's go with a circuit and see how a mutually coupled element works in a circuit. Okay?
Yes. So this is playing is 2 for L and B2.
In here?
Yeah, how is that 2? It's 16.
No, M is 2. Oh. This is 16, this is 2. Period. All right? Okay. All right, let's go ahead and consider this circuit in here and try to work out this relationship, these relationships in the circuit directly. You have a voltage source VA, a 2 ohm resistor. Now, this is the inductor that's coupled to another inductor, and I'll show another one here. Okay? So take a look at the dots. The dots are where the currents go in. Okay? So you can have dots anywhere in the circuit, but in order to use this relationship, I1 and M and I2, you got to have currents towards the dot points, or the dotted points. Okay, so the way I managed to have the currents over here is a little bit critical. Directional current can actually change the solution. So you have to make sure that you got the right currents in. Okay, and the mutual inductance is given as 2 henries. This is 3 henries. This is also 2 henries. All right, I'm going to go with a mesh analysis here. So I have 2 meshes. I need to have 2 currents in there. So let's assume that I have current I1 in here and I2 in here. Okay? And let's go ahead and write KVLs for both meshes. So mesh 1, starting from VA, it's minus VA, start from this point. Okay? Plus, if this is I1, you have 2 I1 that drop across the resistor. you reach this mutually coupled inductor, all right? You need to go ahead and use this relationship over here. Li, L1, di1. I1 has to go towards the dotted point. It's part of that relationship. This I is going towards it. So I can simply say L1, which is 3 Henries, di1 over dt, okay, plus M multiplied by the current of the other one. M is given as 2. D over dt. Now, what is the current that goes to the other one from the dotted point? It's I1 minus I2, right? So I have to put I1 minus I2 here. Okay? That's this element. Now you go to this element to complete the KVL. That's another mutually coupled element. So you got 2 multiplied by d over dt of the current that goes into the node. Remember? L2, I2, and I2 should go into the dot. So the current that goes into the dot here should be placed here. And that's again I1 minus I2. All right? And plus this last term, MV2, empty I1 over dt, M d over dt of the current that goes into the dot point of the other element. The current that goes into this one, which is again I1. So this is your KVL for the first mesh. Second mesh. All right, this is the mesh we're talking about. You have this element first. That's L2, which is even as 2, multiplied by the current that goes in here. The current that goes in here is I1 minus I2. Okay, now, you're moving this direction. The voltage is given this direction. Remember, plus of the voltage is across the inductor, but the plus on the dotted point. So the plus love is there. But you're moving actually this direction. You're having minus this voltage. Put minus sign here. Plus the mutually